All right, so for our discovery problem, we need to take a look at these four graphs. So I have these blown up a little bit here so that you can copy them down. I want to say a couple things. Don't worry about copying this grid out. Draw an x and a y axis, and then sketch the red function out and write the equation. You don't need to have the exact values of your x and y axis numbered out. The important thing is that you have the basic shape, it's where it is in relation to the x and y axis and the function. So for each of these, an x and y axis, sketch of the function, and the function itself. Okay, so we're going to actually introduce some definitions here. So each of the underlined words is being defined, and it shouldn't be too scary. I'm going to walk you through it really briefly, and most of these you actually already know, so it's just be kind of a readdressing of some of it. But some of it you may have not seen. So a polynomial is an expression that can be written in the following form, and don't get too worried about all of this. So first off, notice these a sub whatever, so this would be written, this would be called a sub 0, a sub 1, a sub, and the sub means below, right? And all these are the coefficients of each term. And so for example, in your examples over here, if you look at equation 1, right, the coefficient for the first term is 1. So in that situation, a sub 0 is 1, and for the second term it's 2. So a sub 1 would be 2. And you can go down the line until you get to the very last term, and notice that the last term, a sub n, has x to the 0, because x to the 0 is 1, and so you always finish with an x to the 0 term, and that here in this case would be 3. Okay? And the reason I have this plus and then dot 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 plus is that is just telling you that you go all the way down until you get to x sub 0. So you start with the highest degree, and then you'll have one with the degree lower, and then the degree lower. And so in this case, as you can see in example 1, you start with, if it's a second degree polynomial, because you have a highest degree of 2, and then the next one has a degree of 1, and then a degree of 0, meaning the exponent is 2, and the exponent is 1, and then the exponent is 0. And sometimes you'll see that one of the terms is missing, in which case, of course, that means the coefficient is 0, and so that term got canceled out. Now next, we say that each monomial is called a term of the polynomial. So poly means many, and that's why you have many terms, and a monomial is just one of them. And so if we refer to a certain term, we're referring to a term at just one of the pieces of the polynomial. So I'll go ahead and color code this for us. All right, the degree of each term is the value of the exponent for that particular term. So for the first term, for example, the degree is whatever the value of the exponent n is. And the leading term is the term with the highest degree and should be written first. And you guys should be used to that. In standard form, we always write the highest degree first, then the next highest one next, all the way down until you get to the x to the 0 term. So the leading term in this situation would be this term here. Okay? All right, so with that in mind and that vocabulary in mind, here are some questions for you to think about that will help you expand your understanding of the polynomials that we've looked at already. So quadratics, cubics, quartics, and quintics. Okay, so here are the 4 questions. Now you'll notice that one of the questions asks you about end behaviors. Think about what you think that means, and in the context of each of the graphs, right, what do you think that represents? And then go ahead and give it the common sense answer. None of this is anything that you can't answer without common sense. So go through and answer each of these 4 questions. It's going to be vital to you being able to understand the common theme that we are finding. All right, so taking a look at these, if you are trying to find the functions that have an even degree in their leading term, you're looking at the quadratic and the quartic, or numbers 1 and 3. And what do we notice about the end behaviors of these two functions? Well, end behavior that seems to be like how the function is behaving on its ends. Well, both of these functions have end behaviors that are the same as the other, right? So on one side, the end behavior is the same as it is on the other side. Notice here, the end behavior for both is that they're both increasing, right? They're both getting bigger and bigger as we move out to the left and move out to the right. For the functions with odd degrees in the leading term, the cubic and the quintic, we notice that the end behaviors of these two functions are different from one another. So whatever's happening as we move to the end of the function on the left is going to be the opposite as we move towards the end of the function on the right. Here it's decreasing, getting smaller and smaller and smaller, or not smaller, but more and more negative, and over here it's getting more and more positive. For the quintic, same is true, right? As I move to the left, the end of the function on the left, it's getting more and more negative, and as I move towards the end of the function on the right, it's getting more and more positive. So the end behaviors for the odd degree polynomials are different from one another, whereas the end behaviors for the even degree polynomials are the same as each other. And this is an interesting and important characteristic of polynomials. Okay, so the end behavior of a function is just simply the behavior of the function as it is approaching either infinity or negative infinity. And so approaching positive infinity means you're moving towards the right, and approaching negative infinity means you're moving towards the left. We're talking about the x-axis here. Important to note that this is referring to on the x-axis, so add that into your notes, on the x-axis. And if you are approaching positive infinity, that would be the right end behavior, and as you're approaching negative infinity, that'd be the left end behavior. And so what I want you to think about is why the pattern that you noticed in the discovery problem is the way it is, right? You notice that when you had a polynomial with a odd degree in its leading term, the end behaviors were different. But when the leading term had even degrees, the end behaviors were the same. So I'm actually going to write this question up, and your job is to write at least 3 sentences on why this is the case. Come in with your answer tomorrow, and so that we can discuss and actually nail this down. Okay, so here is your question to think about. Write it down. Think about it, play around with it, try some examples, plug some numbers in. Whatever you think makes the most sense. Your goal is to make a compelling argument that makes sense, and write at least 3 sentences, answering this question. You can have graphs, diagrams, things that you've plugged in as proof, but you should have written at least 3 sentences.